Well, hello, and thank you very much for watching our presentation. We are Team 17, the Rankine file from Spring 2017 Chemi 470 class. My name is Patricio de la Fuente, and these are my teammates.
I'm Raad Mulla.
I'm Zach Morris.
I'm Chiao-Wen Huang.
I'm Ruth, Robles.
And together we designed a conversion plant from sugar to jet fuel. So without further ado, let's get started. All right, so to begin with, our plant was given a problem statement which stated that we had to design a plant to produce jet fuel from sugarcane at a rate of 4,400 gallons per hour. Whenever we started the process, we ran into four main problems. We had a hard time understanding and researching the ABE fermentation process, mainly because it's not something that's widely available or widely used in commercial production plants. Then we also had problems determining the types of reactors that we would need in order to actually make our process work. Additionally, we also had problems modeling our separations because we didn't exactly know how we would separate some things from others, especially because some of them were incredibly similar, as you will see further along in the presentation. Lastly, we also had problems determining this composition of certain streams of ours because we didn't know exactly how chemicals would play with each other after the reactions or after the separations. In any case, Rod will talk to you more about how we actually started our process, as well as how we narrowed down our choices in terms of our process streams.
Good. Thank you, Patricio. So after spending a whole week of surveying the market, we created 6 blood flow diagrams. 2 of them stood out in terms of their pros compared to the other blood flow diagrams. The first one is basically the sugarcane to jet fuel ABA fermentation pathway, as it can be seen from PFD number 5. The second one was the ABA fermentation pathway as well, with addition to the pre-treatment of bagasse pathway. However, our team decided that we would choose number 5 instead of 6 because of how the pre-treatment bagasse pathway relegate the efficiency of our overall plant and increase the cost of the plant significantly. So we moved ahead into designing our process flow diagram that can be seen here with a product stream of 4,488 gallons per hour of biojet fuel. And then this design was separated into 5 different sections. The first one was the 2-pentanone heavy separation section, where we take our sugarcane feed and ferment it, and then take the slurry product into alkylation reactor, and after that we send the product of heavies into a D2 pentanonizer tower that would separate the 2-pentanone in the overhead product contaminated with some CO2, and the bottom product would include the heptanone and the decanone components. Then the second section is a CO2 pentanone separation that will take the overhead product stream from the D2 pentanonizer tower and utilize a liquid extraction drum to remove CO2 from pentanone, and then after that the pentanone will continue on to the trimerization reactor. Now the third part is a 6-decanone heptanone separation, where we take out 6-decanone and sell it with a purity of 99.5% per weight, and the overhead product will continue on into the 2-heptanone 4-heptanone separation section, where we separate the 4-heptanone using a D4 heptanonizer tower, and then the overhead product with mostly 2-pentanone would go to our last section of the plant, which is the 2-heptanone purifier, where we further purify 2-heptanone from 4-heptanone before sending it to the trimerization reactor along with the 2-pentanone, and then after that they would go to the hydrodeoxygenation reactor, which would produce our jet fuel. Now Ruth is going to talk to you about how we estimated the capital cost of our design.
Thank you, Rad. So our plant is expected to be located in Maui, Hawaii. It ended up having a capital cost of $163 million. 2 main portions contribute to this cost, which are the IBL and the OBL as seen in the chart. I will explain the main contributors of the IBL. So the first main contributor is the separation of the 2-heptanone and 4-heptanone. This is a very expensive process because it involves separating two very similar compounds. These compounds have to go to the trimerization reactor, and due to the lack of knowledge of the 4-heptanone, once it goes into the trimerization reactor, our team decided to try to purify this the most possible amount and try to get pure 2-heptanone. This involved one distillation column with about 160 trays. We went about this deciding to get 2 columns instead. Now, each one requires 80 trays, but this, of course, still involves a high utility cost, and they are very big towers. The second contributor for the IBL is a fermentation reactor. 44 reactors are needed in order to make this process continuous. Our team suggests that we would go about this, increases the size of the reactor in order to decrease the number of reactors needed. Now, let's discuss the OBL. The main contributor for the OBL is the utility cost. Next to the raw materials, and then the site development and the environmental factors are hand in hand. Zach will now discuss our base case.
Thank you, Ruth. So in order to move forward on our economic evaluation of the plant, we had to make a couple assumptions for the discount rate, income tax rate, working capital, and etc. So these were given to us by Professor McFadden, and we utilized this to get the cash cost for the plant, which was found to be 48.12 cents per pound of jet fuel. Doing a 5-year analysis of the markets which jet fuel is produced from, we found that there was a lot of stationary, no movement with the sugar price, natural gas price, and sugarcane price within the U.S. However, in the past 3 years, there's been a sharp decline with crude oil prices. This is not good for our biojet fuel product because regular conventional jet fuel is made from crude oil. So with this decrease in cost of crude oil, it's also leading to a decrease in cost for jet fuel, which makes our biojet fuel much more expensive than the conventional jet fuel. This is our economic evaluation sheet, and using this we calculated an ATROR of 15.28% with a product price of 63.5 cents per pound. Now, this is higher than the conventional cost of jet fuel, but it's this high because we have a much purer product than the conventional jet fuel. So we're going to use ours as an additive for lower purity jet fuels. We're going to get 2 byproducts from our process, and they're 4-heptanone and 6-indecanone, which are listed at $3.6 and $175 per kilogram respectively. Now our plant gives us an MPW of close to 28 million. This is not feasible because we had a goal to make it 0. And we can make it 0, but we'd have to lower our ATROR below 15%. It's around 12, and that just won't make it feasible as well. So we're not meeting the hard specs on those. Now, Rita will talk about more economic impacts for our price point of our jet fuel.
Thank you, Zach. So here are the 3 most important factors that will impact our base case price projection. First of all, weather. Since our raw material is sugarcane, the weather will impact the supply of sugarcane, and the raw material price will go up as the weather goes bad. Also, the ethanol supply is also depending on the weather, since most of the ethanol is derived from corn. And the second factor is the natural gas market. Since the hydrogen we use in trimerization is derived from natural gas, when the natural gas price goes up, our raw material price of hydrogen will goes up as well. The third and the most important factor is the crude oil market. As you can see from this graph, the market price of crude oil will impact our jet fuel price, just like Zach said before. The crude oil price will also impact our acetone price because acetone is one of the petrochemicals. Here is the sensitivity study we carry out to see how the crude oil price will impact our profit of the plant. Here, the RMM raw material margin is defined as weighted average product price minus weighted average raw material price. As the crude oil price goes up, our acetone price and jet fuel price will goes up. So the R&M will goes up as the crude oil price goes up. And you can see from this graph, ATR goes up when the R&M goes up. And we expected the future oil price to go up because the production in the US is decreasing right now, and the oil producer, they are negotiating on oil freeze. So if the crude oil price goes up, this will favor our plant. The second sensitivity study is conducted on the size of our plant. Currently, our capacity is set to be 100% in our base case. If we increase the capacity of our plant, it means we need a bigger plant and it will take longer to construct. Therefore, we assume that the capacity over 100 will lead to 4 years of construction time. And as you can see here, as the capacity goes up, our ATRR will goes up as well, which will make more profit. However, if we decrease the size of the plant, then the ATRR will goes down. Following, Patricio will talk to us about the spec of our products.
All right, thank you, Rita, very much. All right, well, as mentioned previously, our plant not only produces jet fuel, our plant also produces two additional side product streams. It produces 6-undecanone as well as 4-heptanone at a purity of 99.5 and 99.7% each, respectively. Now, the price of our jet fuel averaged at 5 years is expected to be 63.5 cents per pound. Now, this is high, but as mentioned previously, we plan to sell it as an additive, so we don't count on it being a problem. 6-undecanone's 5-year average price is expected to be $49.54 per pound. This means that we could definitely make a large profit from it and helps to make our plant even more profitable whether we decide to scale it up or not. Now, 4-heptanone is expected to have a 5-year average price of $1.63 per pound. This as well brings in some additional profit, but not as much as a 6-undecanone. In any case, now that we have described the pricing, I would also like to talk about the major recommendations that our group has for the management team. Now, at this current point, our team does not recommend that the facility be constructed. At this point, we can either meet the ATROR requirement of 15%, or we can meet the NPW requirement of 0. But however, we cannot meet both at the same time. For that reason, we recommend that more additional research is done in order to figure out if we could optimize our process in order to lower our overall price and thus make the feasibility higher, per se. Considering a lower ATROR limit is also something that could potentially make our plant feasible. At this point, we found that if our ATROR was allowed to lower down to 12.02%, we could actually have an NPW near 0, allowing us to actually construct the plant. Now, the last recommendation that we have for management team, although definitely more of a outside suggestion, would be to place the plant somewhere other than Hawaii. Hawaii is, as a state, is ceasing sugar production in its entirety by the end of this year, meaning that our raw material costs are incredibly high, leading to a very high product price, which is not very competitive in terms of making us money. In any case, that sums up our project for you in terms of technical information. However, before we leave, I would also like to give a little bit of a talk about how we believe our team really went about in succeeding the completion of this project. Now, our team is definitely very unique in that we have a lot of really great people. However, we have very different schedules. A lot of us had classes at completely different times, and we only really had 2 or 3 days a week available to work on this project. We believe that with the time that we had and with the resources that we were given, we accomplished the task within the margins of acceptability. We believe that our team succeeded mainly because we were actually able to communicate with each other really well. We were able to coordinate our meetings incredibly well. None of us ever had excessive absences, and we all learned to count on each other in terms of completing the work. And we were also willing to listen and explain each other's ideas. That way we could move forward faster without having to get bogged down with all the different minutiae that the project required in terms of completion. In any case, once again, we thank you very much for listening to our presentation, and we hope you have enjoyed it. In any case, we look forward to talking with you again soon. Thank you very much.